Hello, I'm Mr. Wolf, and welcome to another one of our video lectures. In this one, we will be looking at motion graphs. We will be analyzing them and trying to understand the different parts of each of the equations we will be using. We really want to get down and look at what each part means. So first, let's start with a velocity time graph. Here, I have my graph. I'm going to put velocity along the y-axis, time, it's going to go on the x-axis. So I can write those in right now. Time is measured in seconds. And velocity in meters per second. Let's start by looking at some situation where we have a constant velocity. Some constant velocity of v. Here's some motion with a velocity of some object. It's a constant velocity. It's a straight line. It's not changing. In this case, the velocity is going to be equal to the average velocity the entire way through. Let's say some object travels for some set amount of time, t. Here we have our time t. Now, as we look at this graph, we have some area right here. What does this area really mean? When we look at it, finding the area of this box right here is very simple. It's a rectangle, v multiplied by t. Velocity multiplied by time. What does that mean? Let's look at the units. We have meters per second multiplied by seconds. This is going to give us our answer in just meters. So from this graph, a velocity time graph, we can tell that knowing for a constant velocity, the area under the curve, and actually it doesn't even matter for a constant velocity whether the velocity is constant or not, as we'll see in a second, but the area under the line, between the line and the axis, is going to be our change in position. Now notice here that this is not just merely the final velocity, but in this case, it's the same as our average velocity. So what I'm going to go do is I'm going to write this up here. This is our first equation. V average multiplied by time is equal to our change in position. Change in position is just measured in meters. We can already prove through units that this works out. Let's move on and look at a case where perhaps the velocity is not constant. Let's assume that the velocity starts out at 0 and increases. For this example, we'll say that the velocity increases at a constant rate. As it increases to a constant rate, we know by looking at the slope that the change in velocity that's our change in y, over the change in our x, which is time. This is equal to acceleration. So first, from this graph with a changing velocity here, we can find our acceleration through the slope. Second, let's look at the area under the curve. So we have some time t. This area under the curve is a triangle. So let's look at how to calculate that. Pretty straightforward. 1/2 the base, which is t, times the height. The height, in this case, is going to be v minus v naught. That's pretty short. I'm going to add in some extra steps here just to get to another point. You may have just assumed that it would be v since we said that v naught was 0, but let's just stick with this for right now. This here, we know is our change in position. We also know another equation. By rearranging this over here from our slope, we can say that our final velocity is equal to our initial velocity plus our acceleration multiplied by time. So acceleration, this is how much the velocity changed. This is our initial velocity. Let's substitute it back in here. 1/2 t times v naught plus a t minus v naught is equal to delta x. Go through here, these terms will cancel. And we're left with 1/2 t times a t is equal to delta x. Distribute this through. 1/2 a t squared is equal to our change in position. This is one of the fundamental ideas in physics, that if you're starting at rest, for example, something is dropped off a cliff. So I drop this pen. Its initial velocity is 0. It accelerates to some final velocity. If we're looking at it in a projectile motion form, the distance that it travels, delta x, is merely equal to the acceleration, 1/2 the acceleration, multiplied by the time squared. Let's look at one more case. I'm actually going to erase this up here, and I'm going to put that original, well, whatever. We don't need it up there. One last case. Let's say our velocity doesn't start at 0. We have a constant acceleration, and it increases to some final velocity. That works enough. Now, over time t, I'll write that bigger. We already know that the area under a curve for a velocity time graph is going to be the distance traveled. But it's a little bit trickier to solve for this. So what we're going to do is we're going to break it into two different parts. Part 1, part 2. Part 1, we already know from the first part of this little lecture, is that this velocity multiplied by time is going to give us the area of that, or the distance traveled. So in this case, 1 v naught multiplied by t is equal to delta, or is equal to, well, we have v naught multiplied by t. We're not going to include delta x yet. Oh, you know what? Whatever. Doesn't really matter. We'll incorporate them in a second. Part 2, we're just going to pull up, we know from our last part, it's a triangle. We have our acceleration. We've shown that. So we have 1/2 a t squared. we need to add these both together to get our total change in position. Delta x is equal to v naught multiplied our initial velocity multiplied by time plus 1/2 the acceleration multiplied by the time squared. This should be an equation that you already recognize. This is the significance of each different part. This is how much the object moves due to its initial velocity. And this section relates how much the object moves due to its acceleration. The total change in position is here. We can split that up to put it into the more common form of the equation that you see. X is equal to x naught plus v naught t plus 1/2. Let's write this bigger. So our final position, x, this term signifies our initial position, x naught. This next section here is how much distance was traveled due to the initial velocity, v naught multiplied by t. And this last term here is concerned with how much our position changed due to the acceleration, 1/2 a times t squared. I hope this makes it a little bit easier to understand the different parts of the formulas that we use and the significance of each of those individual sections. Remember when you're looking at your graphs here to pay attention to the important quantities, for example, the slope and area under the curve. Thank you very much. I hope you enjoyed this. Have a wonderful evening.